Okay. We had 22 yes evil eyebrows that could taco tongue, 9 no evil eyebrows that could taco tongue, for a grand total of 31 people that could taco tongue between 5th and 6th period. We had 4 people that could evil eyebrow but couldn't taco tongue, 2 people that couldn't do either. We had 37 people total included in our survey. So let's look down at number 2 then. Given that the person selected is a yes evil eyebrow, what is the probability that they are a yes taco tongue? Given that they are a yes evil eyebrow, what is the probability that they are a yes taco tongue? What'd you say? Yes. You're exactly right. 22 out of 26. When we have a given that, that is the only part that we're going to be looking at. So given that means I already know they can evil eyebrow. So the taco tongues would be 22 out of a total yes evil eyebrow of 26. And then what would 22 out of 26 be as a decimal? 0.85 what?
Oh, 0.846.
0.846, there we go. And so 84.6%. We need to talk about how to write this using proper probability notation, because that is something that you guys will be expected to do. So when I start probability notation, it has to start with what letter? P. So it has to start with a capital letter P. And then we have a parenthesis. And then we have the thing that we want the probability of, not the condition that we were given, but this piece, the yes taco tongue. So that would be my next part. Yes taco tongue. And then we use this line right here to mean given that. Oh, I'm so sorry. That's really zooming in there. Let's fix that. There we go. And this piece right here, this is what I was given that. We call this a condition. Given that, and then followed by the condition. All right. Let's look at part B. Given that the person selected is a no evil eyebrow, what's the probability that they're a yes taco tongue? No to evil eyebrow. What's the probability that they are a yes taco tongue? 9 out of 11, yes. And what would 9 out of 11 be in its decimal form or in its percent form? Yep. 0.818 or 81.8%. What would my probability notation for this look like? P parentheses. Yes, TT. Bar, no, EE. Yes. Here's my given that. Here's my condition. We call these conditional probabilities. A lot of times when we're talking about conditional probabilities, they will use the words given that. Sometimes they won't. And sometimes it doesn't come at the beginning of the sentence. But when you have a given that situation, one of the events that you're looking at, you already know whether it happened or not. So it'll say something like, if this, then what's the probability of this other thing? Or what's the probability of X if Y? That would be another situation where it was a given that. So sometimes they'll use the word if, sometimes they'll use given that. The idea is that you already know about that event. It is no longer a probability, it's no longer up in the air, because we know about it. Based on these two previous answers, 84.6%, 81.8%, what kind of conclusion can we make? Many people can taco tongue. Anything else? Is anybody more likely to be able to taco tongue? Alice, how are you doing this? Tell me why you did that. 1% is greater than the other. If I knew for a fact that the person standing in front of me could definitely evil eyebrow, could I make a better prediction about whether or not they can taco tongue? Yeah. They're more likely to be able to taco tongue if they can evil eyebrow than if they can't evil eyebrow. It's not a huge difference, but there is a difference. So I can conclude that people who can evil eyebrow are more likely to be able to taco tongue than those who can't evil eyebrow. Once you get done writing this down, there's a definition before question number 3. I want you to read that definition carefully. All right, our definition says that two events are independent if knowing whether or not one event has occurred, knowing whether or not one event has occurred does not change the probability that the other event will occur. Are yes taco tongue and yes evil eyebrow independent? No. Why are these not independent? The percents are different. If you know that somebody can evil eyebrow, they're more likely to be able to taco tongue than somebody who can't evil eyebrow. The percents are different. Right. We're going to flip this over on the back next. And I want you to do number 4 on your own. Same idea, different table. So different numbers, but same idea as what we just did. I'm going to give us about, I don't know, a minute and a half, maybe up to 2 minutes to do number 4. So for this table, all my Pike seniors, what's the probability of a yes taco tongue? 80%. 480 over 600, or 0.80, 80%. What's the probability of yes taco tongue given that yes evil eyebrow? 90%, 180 out of 200. What's the probability of a yes taco tongue given no evil eyebrow? 75%, 300 out of 400. Are the events taco tongue, yes taco tongue, and yes evil eyebrow independent? No. Why not? Yep, percents change. If I know whether or not evil eyebrow is a yes or a no, it changes my percents of whether or not it's a yes taco tongue. Right? Suppose, imagine with me for a moment, that taco tongue and evil eyebrow actually are independent events. What was our probability of yes taco tongue? 80%. If these events really are independent, what would the probability for part B be? 80%. What about for part C? That would also be 80%. If these events really are independent, all of those percents will be the same. If my event A given B, and my event A given B complement are all exactly the same, if those are all equal percents, then the event is independent, or the events, rather, are independent. Let's see if we can figure out what the two-way table would look like. I know that 480 out of 600 is 80%. So we have 80% are a yes to taco tongue. What would have to go here then, if this is really independent, so it's different than up above? How many would we have for yes evil eyebrow and yes taco tongue if these are independent events? How much? Sorry, I heard somebody say a number, but I couldn't hear how much the number was, and I'm not sure exactly where I heard it from. It can't be 240 because 160, yes. Let's look at why it's 160. I can't have 240 because this whole thing right here adds up to 200. Oh, you were looking this way, yeah. How did you come up with 160? Multiply 200 by 0.80. This is 80% of 200. So what would have to go right here for yes taco tongue but no evil eyebrow? How much? 320, yes. How'd you get that? You can do that, absolutely. Or what else could you have done? 80% of 400, yes. So you could have calculated either one of those first. All right, let's fill out the rest of the table then. If this is 160 and this column total is 200, what goes right here? 40. What about in that last cell? 80. Nice work. So how can we tell from a two-way table whether or not events are independent? How could I use this two-way table? We just made and forced this two-way table to be independent. But if I was given a two-way table, how could I use that to see if the events were independent? The percents are equal. My conditional probabilities, this out of this and this out of this, are exactly the same as each other, and they're exactly the same as my marginal probability out here, my total. So check to see if the conditional probability of one event stays the same given whether or not the other event occurs. And then down here for number 8, we wrote this down once already, but this is a really important rule. This is how we check for independence. The probability of event A is the same as the probability of A given that B is the same as A given that B complement. Then the events are independent. If the probability of event A does not change when event B does or does not happen. Let's see how well we understand this. I'm going to give you 2 situations, and I want you to tell me, without any numbers, whether or not you think these things would be independent, whether or not you think the probability would change or not by knowing the outcome of one event. The probability that you get an A on the next test, and whether or not you study the night before. Would those be independent events? No. What about the probability of you getting an A on the next test and whether or not I let my cat go outside today when I get home? Those would absolutely be independent events. If you know whether or not I let my cat out, that does not help you at all predict whether or not you're going to get an A on the next test. But if you study the night before, that would change that probability. Right. Flipping it over. Page 13. Conditional probability, the probability of one event happening given another event has occurred. The probability of A given that B, up in my numerator, we have the intersection A and B. We've got both of them going on. That came from one of these. My denominator would be the total for either one of my columns or one of my rows, but not the grand total from the whole group. Because when we're looking at a conditional probability, we're only looking in this group right here. So if you go or look at all the way back at the front side, this number right here is both. This number right here was just my yes to evil eye. So we have both up on top and our condition on the bottom. Oops, I went one too far. My independent events, knowing whether or not one event occurs, does not change the probability of the other event. All right. I want you guys to take, there's 3 questions down below. Take about 3 minutes. Take about 1 minute per question and answer those for me. I want you guys to do the check your understanding. What is the probability of C given that S? 40%. What does that mean in context? Basically, take this notation right here and tell me what in the world that says. Yes. That is 100% correct. Absolutely correct. The probability that she has 4 or more children, given that she was surveyed in 1976. The order of the sentence isn't that important. You can flip it around. Like I had the given that first. That doesn't matter. Given that the mother was surveyed in 1976, there is a 40% probability that she had 4 or more children. So I interpreted the notation here along with what the actual percent was. Question number 2 says, given that the chosen mother was not surveyed in 1976, what's the probability that she had 4 or more children? What'd you say? 0.13, absolutely. How'd you get that? What would the notation look like? Let's start there before we talk about how we're getting it. What would the notation look like for this? Yes.
The probability of C given the complement of S.
Yes. Probability of C given that the complement of S, or S complement. And it is absolutely going to be 0.13. How do we get that 0.13? Let's go back and look at the table. Tell me how we get 0.13. We look at the years that aren't 1976, so we're going to need to look at this year and this year. That's exactly correct. We are going to add the 4 plus children from both of those columns. Why can I just add them? Why don't I have to worry about subtracting anything out? Because they're mutually exclusive. Somebody that was interviewed in 1994 is not part of the same group as was interviewed in 2014. These are no overlapping people. And so then you get 26 out of 200, which is 0.13. Are these events surveyed in 1976 and 4 or more children independent? No. Why not? Probabilities are different. If she was surveyed in 1976, she's more likely to have 4 or more children than if she was not surveyed in 1976. The probability of C given that S is not the same as the probability of C given that S complement. These probabilities are different. The new homework that you guys grabbed on your way in the door is going to be due on Tuesday. I'm going to take this down in just a moment so that we can grade your homework that is due for today. You are going to need a separate writing utensil to do that. You can borrow one from the back table if you need to.